Hello everyone, I welcome you all in lecture 10 of Mechanics of Solids, and we'll be discussing today last numerical regarding module 1 stress and strain, and further we'll go ahead with module 2 shear force diagram and bending moment diagram. So the numerical statement at present discussion is something like this. Numerical 14. A suspended bar system consists of two cross sections as shown in the figure. So the diagram given is something like this. Before application of the force, the lower surface is 1 millimeter above the supporting surface. So this is the surface, supporting surface, and this bottom part is not connected to it before application of the force. So this distance is given as 1 millimeter. Find the reaction of the lower and upper supports. So the reaction over here at the top support and at the bottom support is to be calculated, and the stresses in each section when a load of 50 kilonewton is applied as shown. So 50 kilonewton force is applied at this position, okay, and cross-sectional area at the top is 100 millimeter square. So this cross-sectional area is 100 millimeter square, and the cross-sectional area for second part is 250 millimeter square. The lengths of different parts are given. For first top part it is 1.5 meter, for second part it is 2.5 meter, and for both materials, for both parts, the material is same, and Young's modulus is 200 gigapascal. So to start with, if suppose R1 is reaction at top, over here if this reaction is R1 at top and R2 if it is reaction at bottom, then after elongation of top portion and contraction of bottom portion, reactions at both supports will get developed. So what will happen? Reaction at top and reaction at bottom will get developed when this top portion, it will be getting elongated by 1 millimeter, and then the system will be in support condition, and then reactions will be getting developed. So we'll go through the diagram for this. Say if we have two reactions, R1 at top and R2 at bottom, then R1 plus R2 must be equal to 50 kilonewton force applied, and the free body diagram of structure and members are as shown in the figure. So this diagram is giving us this 50 kilonewton force is applied force, and R1 is supporting reaction at the top and R2 is supporting reaction at the bottom, and members are as shown. So if we draw free body diagram of each member, so we will be having, say, R1, if this is a total reaction over here, then R1 will be equal to 50 minus R2. R2 will be getting developed after this part 2 or bottom part is getting connected with this support, and if R2 is the reaction getting developed at bottom, then this part will be subjected to force R2. So the change in length of two portions will be written with this statement. Elongation of upper portion. So elongation of this particular portion will be delta 1 is equal to P1 L1 divided by A1E. So it is delta is equal to PL over AE. So this first part we are writing it as P1 L1 divided by A1, and E is same for both the parts. So force developed in this top position is 50,000, that is 50 kilonewton converted into Newton, 50,000 minus R2, and the length of that is given as 1.5 meters, so it is 1500 mm divided by area of cross section is given as 100 mm square, so 100 into 200 into 10 to the power 3 megapascal. So this is contraction of bottom portion will be then delta 2, and that will be P2 L2 whatever force getting developed in the bottom portion, and divided by A2 into E. So if R2 is the reaction getting developed at the bottom when this part is getting connected, then R2 into L2, so that's length is 2.5 meters, so it is 2500 millimeter, and divided by its area of cross section is 250 millimeter square, and its Young's modulus is again same 200 into 10 to the power 3. So what statement we can write further with the compatibility condition that elongation of upper portion, so elongation of this top portion minus shortening of lower portion is equal to net elongation. So net elongation taking place is 1 millimeter because this elongation is permitted. 1 millimeter elongation is permitted, and whatsoever elongation of upper portion is taking place minus whatsoever shortening of lower portion is taking place, because whatsoever elongation of upper portion and the shortening of lower portion, the difference between these two is this 1 millimeter, which is not connected part of the structure, and this bottom support. So with this, what we can write is this elongation of upper portion is written over here as delta 1. So this we have written as 50,000 minus R2 into 1500 divided by, so this particular term over here, once again we have written it, and minus this shortening of lower portion, that is delta 2, that is written over here, and 1 mm as it is. So with this equation we can calculate this R2 by calculating it. So it gives us R2 as 22,000 Newton and R1 as 28,000 Newton. So total together is 50 kilonewton or 50,000 Newton. Now with this you can go for calculating the stresses at the top portion and stress at the bottom portion. So stress at the top portion will be, now you can calculate it as at top portion you have R1, so that will be R1 divided by A1, or the area of cross section of that. So it is 28,000 Newton divided by 100, so that gives 280 megapascal or 280 Newton per millimeter square. So similarly we can calculate what is stress getting developed in bottom portion, as stress in bottom portion equal to P2 divided by A2 or R2 divided by A2. So we have a reaction at bottom as 22,000 Newton. So 22,000 divided by 250 millimeter square, its area of cross section. It gives us stress in bottom portion as 88 megapascal. So with this numerical we will go further with module 2, that is axial force diagram, shear force diagram, and bending moment diagram in beams. And to start with actual discussion regarding SFD and BMD, we will go through few prerequisites that we have discussed already in first year subject called engineering mechanics. In the course engineering mechanics, we have studied about different types of supports used in beams. One type of support is roller support. The symbol used for roller support is as shown in this particular diagram, and number of reactions getting developed in case of roller support is one support which is perpendicular to the supporting system on which those rollers are being kept. So that kind of support system is called as roller support. Another type of support we have discussed was hinge or pin support. The symbol used is something as shown in this particular diagram, and in case of hinge support we will be having two reaction components, horizontal reaction as well as vertical reaction, and in case of third type of support, which is called as fixed support, the symbol used is something as shown in this particular diagram, and the number of reactions getting developed will be three reaction components. One will be horizontal reaction, the second will be vertical reaction component, as well as there will be a movement as a reaction getting developed. So these reactions are actually not permitting that kind of deflection to be taken due to the applied external forces. Again, we will discuss it about that in types of beams. So most common types of beams are these simply supported beam. The diagram is something like this. So what is shown over here is at this joint A, this is a hinge support, and at joint B it is a roller support, and it is subjected to some external force in between. So what will be the reactions and deflected shape? So probable deflected shape will be as shown in this particular diagram, this red color. And due to the two reactions or two reaction components at this joint A, now the vertical deflection and horizontal deflection is not permitted at this joint. Over here at roller support, there is one reaction which is vertical, so this deflection is not permitted. But rotation at this joint, at this particular two joints, this rotation is permitted. And in case of another type, it may be simply supported beam and some part of that may be overhanging. So the diagram may be as shown over here. So this part beyond this support B is called as overhanging, and the deflected shape, probable deflected shape, it may be something like this. So try to understand difference between these two. This kind of the deflected shape is called as sagging. Over here in between these two supports from A to B it is sagging, and beyond that this is called as hugging type of deflection. The third type of beam that we have discussed in course engineering mechanics was called cantilever beam, and the diagram is something like this. One of the support is fixed support and another support is free, and then the probable deflected shape, it will be something like this. Okay, so now you can understand what is that third reaction taking place over here. So that moment reaction getting developed in case of fixed support is not allowing this kind of rotation which is permitted in case of simply supported beam or in case of overhanging beam. This rotation is not permitted at this end, and the difference between this deflected shape and this deflected shape, in case of simply supported beam, this is called as sagging type of deflection, and in case of this cantilever beam, this kind of deflection is called as a hogging type of deflection. So further we will discuss about equations of equilibrium that we have already discussed in engineering mechanics. So a structure or one of its members is in equilibrium when it maintains the balance of forces and movements due to forces. These equations of equilibrium be satisfied along the three independent axes as summation of forces in x direction equal to 0, summation of Fy equal to 0, and summation of Fz equal to 0. And so also the movements about x, about y-axis and about z-axis due to the applied forces must be equal to 0. So in case of a single plane structure like beam, if the loads are coplanar, then the equations reduces to summation Fx equal to 0, summation Fy equal to 0, and summation of movement of all the forces about z must be equal to 0 about any point. So in case of plane structures, we have three equations of equilibrium: summation Fx equal to 0, summation Fy equal to 0, and summation m about any point must be equal to 0. So further, summation Fx and summation Fy represents the algebraic sums of the x and y components of all the external forces acting on the structure, and summation mz equal to 0. What it represents is represents algebraic sum of movements of components of all external forces about z-axis about any point of the structure over the xy plane. Further, we will discuss about exactly what we understand by free body diagram. For the analysis of structure or member, it is necessary to draw its free body diagram. A member isolated from its supports and surroundings and the external acting force or couples, etc., with reactive forces are shown in those diagrams. If a free body diagram of a member is to be drawn, the part of member either to the left or right of the section is to be drawn with externally active and reactive forces and the internal forces getting developed due to that particular externally applied forces. Generally, at a particular section, there will be internal forces which are normal force, which is axial force, or the shear force and the bending moment. So we will go through the diagram regarding this. Suppose you have a simply supported beam as shown in this particular diagram and a section in between at point C over here. And if I want to draw a free body diagram for this particular part of the complete beam, so if I am taking section over here at C and if I am considering this part from support A up to point C, then the free body diagram may be something like this. Okay, so at A we have hinge support, so two reaction components are there, vertical as well as horizontal. Some part of the loads acting on in between that position and the internal forces. The internal force may be axial force and it may be another vertical, it is shear force, and there will be some movement getting developed due to these active and reactive forces. So that is movement, or generally we discuss now as bending movement. And if we consider this part from position C up to point B or up to this support, so these internal forces may be the shear force, axial force, and the bending moment as earlier. So these are the internal forces which are for equilibrium of that particular structure internally. And now these three internal forces must be making equilibrium of this part if we consider the reactive and active forces in that particular part of that particular structure. So with this discussion, we'll go through the introduction to what exactly we understand by shear force and what is bending moment at a particular section in case of analysis of beams. So shear force is the unbalanced vertical force on one side of the section. It may be considering either to the left or to the right of that particular section of that beam. So it is the algebraic sum of all the normal forces on one side of the section. A shear force diagram, SFD, generally we will be discussing henceforth. It shows the variation of shear force along the length of the beam. So what we understand by shear force is the unbalanced vertical force on either left of a particular section or right of a particular section of that particular beam. And it is algebraic sum of all the forces either on that particular part. It may be left part under analysis consideration. So it is the algebraic sum of all the normal forces on one side of the section. It may be either to the left part of that particular section or right part of that particular section. And the shear force diagram shows the variation of shear force along the length of the beam. So for a complete beam, how the shear force is changing from a particular section to the another section, or from a point to another point, that diagram will be drawing as a shear force diagram. Generally, the sign convention used is something like this. So if we are considering a section in between at a particular position on a beam, then the left part upward forces will be considering as positive, and if we are considering a section and if we are considering right part of the section for the analysis, the downward forces will be considering as positive shear force. So it rotates clockwise. It rotates the segment generally. For the analysis of shear force, the sign conventions used are something like this. So suppose if I am considering a section somewhere over here, and if we are considering the left part of the section and the forces acting on left part of that particular section, then the upward forces will be considered as a positive shear force. And if we are considering for the analysis right part of the section, then the downward forces on right part of the section will be considered as positive shear force. So these kind of forces which are rotating that segment clockwise, that is termed as a positive shear force. Or the otherwise, if we are considering a section somewhere like this and the left part of that particular section, then the forces which are downward will be termed as negative shear force, and the forces on the right part of the section which are upward will be considered as negative shear force. Or these kind of shear forces are trying to rotate that segment in anti-clockwise sense. So this sign convention is positive shear force, and this sign convention is for negative shear force. So we'll go through what exactly we mean by bending moment. Bending moment at a section on a beam is defined as algebraic sum of the moments of all the forces about the section, considering forces acting either on the left side of that particular section or right side of that particular section. So a bending moment diagram is, as discussed in shear force diagram, it is a variation of the shear force. Bending moment diagram is showing the variation of bending moment along the length of the beam. So generally sign convention used is something like this. So what we discussed earlier, this kind of deflection is called as the sagging deflection. So the bending moment which is sagging is will be considering it as positive. So positive bending moment which is sagging, creating a tension at bottom and compression at top. So if we are considering a cross section in between, so due to this kind of deflection, it will be creating tension at bottom and compression at top. So that kind of bending moment is called sagging bending moment, and that will be termed as positive. And the another type of bending moment which is hogging, if the deflection is something like this. So this is called hogging bending moment, which is creating tension at top at a particular cross section. It will be creating tension at top and compression at bottom, and that will be termed as negative bending moment. So with this discussion, we will go further with one simple numerical. The statement of the numerical is something like this. Analyze the simply supported beam as shown in the figure, and hence draw shear force diagram and bending moment diagram. So beam is like this. This support A is hinge support and support B is roller support. Distance between A to B is L, and the point load is applied P at point C, which is at the midspan of this beam of span L. And initially what we need is to develop a free body diagram as shown in figure. So now we are aware that at hinge support we will be having two reaction components, and at roller support we will be having one reaction component. So with equilibrium equations, if we apply summation Fx equal to 0, there is no horizontal force as such. So the reaction HA at support A will be 0. With summation Fy equal to 0, we have two vertical reaction components, VA at A and VB at B. So VA plus VB, and the applied external force is P. So VA plus VB minus P must be equal to 0, or we can write equation like VA plus VB is equal to P. With this, by applying the summation M about a particular support equal to 0, if suppose for example if we take summation M about A equal to 0, then for this force P, its moment about A will be P into L by 2, and the moment of reaction VB at A will be VB into L. So the equation will become P into L by 2 as it is clockwise, considering it as plus, and moving due to VB, that will be VB into L anticlockwise. So P into L by 2 minus VB into L must be equal to 0. So with this we can calculate VB as P by 2, and if we substitute this VB over here in the summation Fy equal to 0 equation, so VA will also be P by 2. So knowing these reactions, we can go further for calculating shear forces at different points. So in between A to C, there is one force due to reaction, and beyond C up to B, we have two forces. One is this reaction as well as the applied external force. So necessarily we need to consider two different cross sections. So we need to consider two different sections, as section 1-1 in between point A and C, and section 2-2 in between point C and point B. So first part for calculations of shear force, considering section 1-1 in between points A and C at a distance x1 from A. So this is section 1-1 at a distance x1 from A, and if we are saying that this section is applicable from A to C, then limits with origin as A will be 0 up to L by 2. So for this, if we write the equation, what we have discussed earlier is shear force at a particular section is algebraic sum of forces either considering left part of the section or right part of the section. So if we consider left part of this section 1-1, so we have only one force, that is reaction at A, and that is P by 2. So equation will become SF11, that is shear force at 1-1 section is equal to P by 2. And this sign convention we have considered. If we are considering left part of the section, and if the force is upward, then that will be considered as positive. So with this, if we substitute value of x1 as x1 equal to 0, so in this equation we have no term x. So if we put x equal to 0, then shear force is P by 2, as well as at point C, if we put x equal to L by 2, shear force is P by 2. Further, if we consider section 2-2 in between C to B, then at a distance say x2 from A. So with A as origin, now if it is at C, then distance x2 becomes L by 2. And if we go up to B, then that distance x2 will become L. So if origin is A and section is 2 in between C to B, then the limits for the equation will become L by 2 up to L. So with this, equation can be written as SF22. Now if we are considering section over here at 2 in between C to B. So at the left of section 2 we have this reaction at A, that is P by 2 upward. So that is positive P by 2, and one more, that is external force P force acting at C, and it is downward. So that is taken as negative. So P by 2 minus P is equal to, so that gives us minus P by 2. So if we put now these limits, so shear force at C with x2 is equal to L by 2 becomes minus P by 2. Similarly at point B, if we put x2 as L, as x2 term is not there in this equation, shear force again it gives minus P by 2. So with these calculations, we can draw a shear force diagram as shown in this particular figure. So at A, we calculated the shear force as positive P by 2. At point C, with first equation, we calculated the shear force at C as plus P by 2. And with second equation, at point C, the shear force is minus P by 2, and at B, shear force is minus P by 2. Now, there is no x term in both the equations. In SF11 equation as well as SF22 equation, the term x is not there. Or else what can be discussed as the power of x over here is 0. So, it is a horizontal straight line in between A to C as well as from C to B. So, again we will discuss how to draw this diagram with calculations of bending moment. So if we go further for calculating the bending moment, and if we consider section 1-1, so considering section 1-1 in between points A and C at distance x1 from A. So again this section 1-1 at distance x1 from A, and if origin is assumed as A, the limits will become, if this section is at A, x1 becomes 0, and if this section, if it is at C, then x1 becomes L by 2. So limits for the equation will be 0 to L by 2. Now again try to understand what we discussed about bending moment at a particular section as algebraic sum of moments of all the forces, either considering left forces or the forces acting at left part of that particular section or right part of that particular section. So if we consider left part of the section, we have only one force, that is reaction at A. So that is P by 2, and now the perpendicular distance between these two, that force and section 1-1 is x1. So equation bending moment 1-1 becomes P by 2 into x1. Now if we put these limits, if we substitute x1 as 0, that will give us bending moment at point A. And if we put limit L by 2, so that is the distance of x1, that is point C. So if we substitute x1 as L by 2, we will get bending moment at point C. So if we calculate that, at point A, x1 is equal to 0. So with this bending moment becomes 0. And with x1 is equal to L by 2 at point C, this bending moment will become P by 2 into L by 2. So this gives us PL divided by 4. Now with section 2-2, if we try to go through that, considering section 2-2 in between points C and B at distance x2, and again if we are considering that origin is A, then from A to C that distance is L by 2. So for x2, the limits becomes L by 2 and L. So equation can be written something like this. Now at the left of that section 2-2, we have two forces. One force is P by 2, that is reaction at A. So due to this reaction, we will be having a bending moment as P by 2 into x2. So this is first term, P by 2 into x2, and this is clockwise, and this P externally applied force, that distance up to section 2-2 becomes, this total distance is x2, and from A to C that distance is L by 2. So remaining distance between point C up to section 2-2 becomes x2 minus L by 2. So moment due to P up to section 2 will be P multiplied with x2 minus L by 2. So this is the second term. Now in this equation, if we put the limits, so at point C, x2 is L by 2, so bending moment again, what it will happen? Now this term will be L by 2 and this is L by 2. So this term becomes 0. So this gets cancelled and P by 2 into L by 2. Again this will give us bending moment at C as PL divided by 4. And if we put another limit that x2 is equal to L at point B, now what will happen? This will be P into L divided by 2. And over here, this is x2 equal to L. If we substitute L minus L by 2 will give us L by 2. So this PL by 2 minus this second part PL by 2, it will give us bending moment at point B is equal to 0. So at 3 different points we have calculated the value of bending moment. At point A, bending moment is 0. At point C, bending moment is PL by 4. And at point B, bending moment is 0. Now, how to draw that bending moment diagram is as shown in this particular diagram. So, at A, it is 0. At C, it is PL by 4. You can draw this. And at B, it is 0. And now, if we go through these equations, Bm11 or Bm22, power of x is 1. So this line will be inclined straight line from A to C as well as from C to B. Okay, so this is to be understood that variation of shear force diagram and bending moment diagram, how to draw it is dependent on power of equation, and the graph will be horizontal straight line if power of x is 0, and if power of x is 1, the variation will be inclined straight line, and if power of x is 2 or 3 or n, then variation is second or third order parabola. So that is to be understood. And then with this numerical we will conclude this lecture, and with next lecture we will go on discussing about another standard cases like simply supported beam subjected to throughout uniformly distributed load, how the shear force diagram and bending moment diagram, and what will be value of maximum shear force and maximum bending moment. Likewise for cantilever beam subjected to point load at free end, and cantilever beam subjected to uniformly distributed load on entire span. So those cases we will discuss in the next lecture. I am thankful to you all for this particular lecture. Thank you.